All right, so hopefully you've all figured out how Canvas works so far, but there was an announcement that was sent out earlier a few days ago. So if you click on announcements, then you should be able to see all of the announcements. Now, I know sometimes when you only read the announcements in your email, it might miss a few things. I've tried to keep it mostly text, so hopefully you're not missing anything. But if we take a look at the announcements for this week, just a few things I want to make sure everybody is aware of. So first things first, congratulations on making it through a very intense first week of class. 151 is a really challenging class, and it's even more challenging when we're taking it not during the regular semester. So a few housekeeping things. First thing is that tomorrow is your last day to withdraw without getting a W on your transcript. So if you feel like the first week has been really tough and, over the weekend it just wasn't making sense still, you still have until tomorrow to withdraw. And after that, you have until July 17th to drop the course. Now, if you drop between the 24th and the 17th, you are going to have a W on your transcript. So definitely something to think about. Maybe talk to a STEM counselor and kind of see what their perspective might be. If your current grade is a C or lower right now, and here's the more important part, and you've not made some serious change in how you're going to approach this class. I know some people have been able to shift their work hours to the weekends or have reached out to the tutoring services, etc. If you're not making those changes and you have a C, my suggestion would be to withdraw. This is a challenging class, and I think it definitely takes a lot of time and commitment to say, hey, I'm really going to do this despite not a great start. Okay. So exam number 1 is going to be on Wednesday. So on Wednesday, you're going to have, we will not meet for lecture, okay? But you will have an exam that covers 9.1 through 9.6. Now, the lecture materials, including the notes and the videos and the quizzes, are all meant to give you practice in the concepts. So I think you should find that the test is very well aligned to the material that we've seen in class. Okay. I do want to emphasize that I expect you to use methods learned in class. So I'm starting to see some folks who are doing some different things on the quizzes. And again, I'm going to say there are certain strategies that we're learning in this class because they are in the scope of the curriculum of this class. And so if you're choosing to use another method, you might not be demonstrating the skills that were expected to be able to demonstrate in Calc 2. Okay. I'm also going to really encourage you to show your work and your thinking. Some folks have been doing an excellent job on the quiz in the sense that it's annotated, they've got all their steps there. It's very easy to follow their train of thought. On the other hand, there are some people who are showing like 1 step and then skipping like 5 steps and then writing down another step. And so if you are in that boat, you've gotten that kind of feedback on your quiz, please make sure that you are looking over the quizzes that you get back in Canvas so that you can make adjustment for exam 1. All right, 2 more announcements. The quizzes. So I know that there are a lot of folks who are trying to work and have a life and have a family and take this class and maybe take other classes, and it's a lot. And I just want to say that I recognize that. And so because of that, I'm moving the quiz deadline. So what this means is that quiz number 3 is going to be due at 9:30 a.m. on Wednesday, and quiz number 4 will be due at 9:30 a.m. on Friday. Okay. So instead of the quizzes being due at midnight, they will be due before class on Wednesdays and then by 9:30 on Friday morning. Okay. I hope this gives you some extra time to kind of put forth a little bit more into that quiz, especially if you're feeling really rushed for time. I hope that this adjustment will help you out with that. Okay. One last note about the quizzes. So when I look at your quizzes, I'm looking at these quizzes as to see what kind of things we as a class are doing well and that we understand, and what kind of things as a class we're not really getting. And so if I see work that seems kind of suspicious, in the sense that your work is vastly different from the work that you've shown before, it is definitely something that I am concerned about and something I'm keeping an eye on. So if your plan is to just kind of cruise through with the quizzes and then do super well on the exams, please know that you are asking to be on my radar about whether or not that work is your own. Okay, so I do expect you to put forth the work in the quizzes. The quizzes are designed to help you prepare for the tests so you know what to expect, okay? The last thing is this: we are in week 2, and this week we're going to be covering 9.5 today. We're going to cover 9.6 tomorrow. I think tomorrow will be a little bit of a lighter lesson, so we probably won't go for the whole 2 hours tomorrow, which will give you a little bit of extra time to work on that quiz as well as prepare for your exam, okay? So on Wednesday, again, we are not meeting in person, but you're gonna have an exam. You'll have 24 hours to work on it. You can definitely email me for clarifications on some wording or things like that. That's totally fine. And then on Thursday, we're gonna start chapter 10. We'll start with 10.1. Okay, so every week you can expect to see announcements like this. You guys have been super, super good about reading emails and stuff like that. So just make sure that you continue to do that and you don't miss out on any important announcements, okay? Yes, so the exam 1 is due at 9:30 a.m. on Thursday morning, okay?
I have a question.
Yes.
So like for the exam, you're not going to open it until like Wednesday around a specific time, or are we able to open it whenever we want, like only get 24 hours, or like how does it work?
9:30 a.m. on Wednesday, it will open.
Okay, great. Thank you.
So if you want to spend 24 straight hours working on this test, you got 24 straight hours. You shouldn't need 20.
Yeah, straight off.
Yeah. Okay. All right, and one last thing. Let's go to the assignments. So you know where to find all your quizzes, all the quiz assignments, but you should also be able to click on this exam 1. So I just want to click on this because I added some text to this and I want to make sure that we all have read this. So on Wednesday, we're going to have exam 1. A few things. You can have a cheat sheet for this exam. It is meant to be a way to help you sort of synthesize all of the things that we have studied over the last week. It can be 2 sides of an 8.5 by 11 sheet of paper, and it is the only resource that you are allowed to use during your 24-hour period, okay? So once that exam starts, like, you have 24 hours with only that cheat sheet, not with your other resources, okay? Aside from this, like I said, the exam is not open notes, it's not open resources, it's not open friends, all right? If you get caught cheating, you will earn a 0 on that test and you will forfeit your right to have the final exam replaced your lowest test grade, and that's it. So if that puts you in a situation where you're not gonna be able to pass the class, that's on you for making a decision that I hope you don't make, okay? This test is not a calculator test. So please make sure that you know, like, you trust your mental math and that you can work with some simple fractions and things like that, but it is a non-calculator exam, all right? What this does mean is I better see your calculations worked out. So if you don't have your calculations worked out and you have numbers that magically appear from somewhere, I'm going to be wondering where those numbers came from, okay? There is an opportunity for extra credit on this exam. So there are some questions where it'll be like, choose 2 out of the 3 to answer. You can answer the 3rd one as an extra credit opportunity, okay? That will be counted up to 5 points on that exam. Logistics we already talked about, and the last thing I want to point out is the statement of integrity. So with this statement of integrity, on the front of your exam, there will be this statement, okay? And so what I need you to do, there's a space on the cover for you to hand write out the entire statement, and then I need your signature next to this, okay? If you don't have this on your exam, 0. So make sure that you have this, make sure that you attach your cheat sheet. Everything goes in a single file, upload it to Canvas, just like you've been doing with the quizzes, and then make sure that's all in by 9:30 on Thursday morning. All right, I see a couple questions in the chat, so let's check those. The cheat sheet is front and back. Yes, double-sided. So you can use front and back if you're doing things on paper, or if you're using a tablet, you can use 2 sheets of paper on a tablet. Yes, yes. So if you do your work, and it doesn't matter if it's on an iPad or on paper, please make sure that you show your thinking, okay? Show it in an organized fashion, and if you do have your calculations separate, some of you have been super great on your quizzes, because I know some of those questions are long. You said, like, please look at the sheet attached for this, and I do really appreciate that, because it helps me understand your process as you're going along, okay? Good questions. So do you have to show the FOIL process? I think one of the things that you've already been telling me as I look at your quizzes is the kinds of steps that you can and cannot skip. So everyone's has kind of been a little bit different, and I think it's important that that same level of work be shown on the exam, if that makes sense, okay? I know some of us can FOIL in our head, so we don't need to show that step, and some of us forget to FOIL, so maybe we just need to make sure we write out those 2 side by side. The cheat sheet does not need to be handwritten, so if you want to type things and print it, that is absolutely fine. If that helps, you can kind of shrink the font a little bit, make things smaller, but don't make it too small so that you can't read it yourself, okay? All right, any other questions about the exam or about this week before we get started? Well, if things come up at the end, please ask, and I'd be happy to answer those questions, okay? So I'm gonna stop my share, come back to the screen. All right, so today we are gonna be taking a look at 9.5, okay? So I'm gonna go ahead and share my other screen so we can take a look at those blank notes and take a look at things that we know, what's new for this section, and then work through a bunch of examples, okay? All right, are folks able to see the screen?
Yeah.
Yeah, okay, awesome, thank you. That's always like, not my worst nightmare, but one of them where I'm like, oh, no, I'm gonna be doing all this talking and it's not even gonna be showing up on the screen. Okay, so this section is called integrals using or involving quadratic equations, okay? And what that is code for is we are gonna be looking at using a technique called completing the square, okay? Completing the square is one of those techniques that I think sometimes gets skipped in like high school, hopefully gets covered in pre-calc here at community college, but is definitely a skill that is super, super helpful in a lot of different aspects, okay? So completing the square is going to be sort of our algebraic foundation for today, whereas on Thursday, we were doing like partial fraction decomposition as our algebraic base, okay? So let's get started with what we know. All right, so we've got 4 examples here of things that we know. And when we take a look at these two, I just want us to kind of think about the different strategies that we might use, okay? So for this first case right here, what strategy might we be able to use to find this first integral?
U sub.
Yeah, exactly, U sub, all right? So this one, we should be thinking, let's use U sub. And to be more specific, we can use U equals x squared plus or minus a, and then our du is gonna equal 2x dx. And then one thing that you may have noticed is that a lot of our answers have sort of this 1/2 as part of the coefficient. And that's because if we have that squared and we take the derivative, we end up with this factor of 1/2 that we have to take care of, okay? So when we see a situation like this, we're thinking U sub. What about for the second fraction? Integral of 1 over x squared plus a squared. What makes that one maybe different than the first one, and how does that change our strategy?
Because it's the 1 instead of
Inverse tan?
Yeah, it's the 1 over, exactly. It's not an x, so this is not x. And you're right, it's going to give us a inverse tangent situation. So we're going to have, I think I actually used green. 1 over a, the integral, or no integral, sorry, arctan of x over a plus c. All right, so that would be an example of something where you don't have to show me the work, though for your own benefit, it might be nice to write out what a equals so that you don't make a mistake with that calculation, okay? But when we see these first two, we want to be able to differentiate, is it U sub or is it going to be arctan, okay? Now, for the third one right here, all right, we've got 2x plus 3 over 4x squared plus 12x minus 1, okay? Now, this one is actually a situation where we could also use U sub, okay? It's not as common as terms of what we've seen, but we could use U sub for this one, and let's kind of see how that might work. We could let our U equal 4x squared plus 12x minus 1, okay? And that would make our du equal to 8x plus 12 dx. And what I can do is factor out a 4 to make it match this numerator. So it's almost like another way of asking the first integral, where I have an x over x squared plus or minus a. So this looks like du equals to 4, 2x plus 3 dx, and we would have du over 4 equals 2x plus 3 dx, okay? Now, some of you might be wondering, like, well, why wouldn't I use partial fractions? Because we just learned that on Thursday. And the answer to that is, when we're looking to use partial fractions, the number one thing that we want to look for is not just that it's a quadratic or cubic, but more specifically, the question is, can you factor it? Okay? Can you factor the denominator in a way that helps you set up partial fraction, okay? So if we think about this second one right here, and this one, okay, is a case where we're going to use partial fraction decomposition, all right? And again, our question that we're asking ourselves is the denominator factorable? All right. Now, I think one of the toughest things about learning all these different techniques is I'm sitting here telling you, oh yeah, try this technique, and it can be overwhelming to the point where you're like, well, how do I know? And part of it is I'm trying to highlight some like characteristics that help us make those decisions. And then the other part of it is we just got to practice a lot of different types, and we have to practice the decision making, okay? So let's kind of take a look at the 6 examples in the right-hand column for what's new, okay? So when we're looking at what's new here, I notice that these quadratic equations, all right? So I have an x squared minus 6x plus 13. That's not factorable into whole numbers. I look at x squared plus 8x plus 24, and I can't factor that. I would have to use a quadratic formula. And that same thing is going to be true for all of these quadratic situations, that we're not going to be able to factor it. It's either an irreducible quadratic, or it's a situation where we have to use the quadratic formula, okay? Now, I know some of us love that quadratic formula. It works every time until you make some sign mistakes, then it doesn't work. But what we're learning here is a way to take care of the fact that it's not factorable the way it stands, okay? So let's take a look at, before we get to these first examples, let's review what it means to complete the square, okay? Now this technique is going to be really useful not only for this section and for Wednesday's test, but we're going to continue to use completing the square in chapter 12. And so that would be really important for you to make sure that you get this skill so that we can use it again in chapter 12, okay? If any of you recently took pre-calc, you looked at conic sections like ellipses, hyperbolas, parabolas. We use a lot of completing the square. And so this technique is definitely going to help us out when we do completing the square with those conic sections, and then layer on some calculus on top of that, okay? So let's get started with our completing the square, okay? So when we are completing the square, our job, our mental goal is to think about how could I represent something as a perfect square? And so what that usually looks like is sort of an x minus a squared situation. That's what we're trying to extract from our equation. So the easiest way to kind of think about this as a process is I group the x squared and my linear term. So my ax squared and my bx, I group those separately from the constant. So in my head, I'm doing something like this: x squared plus 6x in parentheses and then plus 11. Now what I'm going to do is think about how can I turn this into something that is a perfect square. And I probably should write plus or minus here, okay? It could be a plus, it could be a minus, depending. And so I think about this as x squared plus 6x plus something, okay? So if I have 6x as my linear term, what is half of 6?
3 square.
Yeah, half of 6 is 3. So I'm going to halve this. So divide by 2, and I get 3. And then I'm going to take that number and I'm going to square it. And that gets a plus 9. Now what that does is create a perfect square out of the first part, okay? Now don't forget about the rest of your equation. You've got this plus 11, but if I only add this plus 9, I've changed my whole equation. And so what I need to make sure I do is sort of counteract that 9 that I added and subtract 9. So this +9 and this -9 balance each other out. And if I were to simplify all of this, I would be able to get back to my original. So it's just a different way of writing your original quadratic. And so what I can do from here is take the thing in the parentheses and write it as x plus 3 squared. Okay, x plus 3, if I FOIL it out, squared will give me x squared plus 6x plus 9. And then I need to add these two. So 11 minus 9 gives me the 2. Okay. So we've taken this x squared plus 6x plus 11. We've completed the square and rewritten it like this. Okay. So let's try the same thing with example number 2. Okay. So I'm going to go ahead and group my quadratic and my linear term. And I'll get x squared minus 18x plus 80 on the outside. And x squared minus 18x, okay, half of negative 18 is negative 9. So negative 9. And when I square negative 9, I get plus 81. Okay. So I have this plus 80 on the outside, and I need to make sure to subtract 81. Because I've got this plus 81 and the minus 81. And so if I complete the square, it means I need that x plus or minus a squared. And in this case, it'll be x minus 9 squared. And then 80 minus 81 gives me minus 1. And I have completed the square. Okay. Any questions about completing the square as a process? Okay. So with that then, oh, I see a question, 2 questions. Okay, so Patrick asked a really good question. He said, is it the same if there's a coefficient for x? If there's a coefficient for x, I typically factor out that coefficient so that I can use this trick of cut that middle number in half and then square it, okay? So what I mean by that is if we had like 2x squared plus 12x plus 11, I would group this as 2x squared plus 6x minus 11. And then I'd be able to complete this square, okay? But let's see what that changes, because I've got 2x squared plus 6x plus 9. But if I subtract 9 here, that would actually be wrong. What do I need to subtract instead?
18, negative 18. I mean, minus 18.
Exactly. I need to subtract an 18. Okay. So the coefficient is important in terms of what it impacts. Whatever this number is, you have to multiply it by that coefficient to get the number you subtract. Okay. If the number is negative, do we square the negative or have the answer be negative? Like, do you mean in this case, how that's a negative 9? Okay, so if it's a negative 9, that negative comes down in here. That's going to be a negative. But when you square negative 9, that's going to be an 81. So that's why we still subtract it outside, because once we square that negative number, it becomes positive. So let's go ahead and try using this algebraic strategy in a integral, okay? All right, so we've got this first example here. We've got 2x minus 1 over x squared minus 6x plus 13. And so when I see this, I first check and say, can I factor that denominator? And in this case, I cannot factor that denominator. So because I can't factor, I'm saying not using partial fractions, okay? If I cannot factor it, my backup strategy is completing the square. All right, so if you can factor it, do partial fractions. If you cannot factor it, try completing the square, okay? So let's go ahead and see what happens. So I'm gonna leave the numerator alone. And like I did in my two previous examples, I'm gonna group my ax squared plus bx terms separate from my c term. Okay. And then I'm going to go ahead and think, how can I make that thing in the parentheses a perfect square? And so I'm going to go ahead and say x squared minus 6x. Half of negative 6 is negative 3, and negative 3 squared is 9. So I have a plus 13 from before, and then I have to subtract 9 at the end. Okay, so let's go ahead and clean that up a little bit so we can see that perfect square. We've got our numerator, which is still untouched. In our denominator, we've got x minus 3 squared. And then we want to make sure that we add and subtract carefully. 13 minus 9 gives us a plus 4. Okay. So this whole top line is just the completing the square part. Okay. All right. So now what we're going to do is we're going to go ahead and do a little u sub situation, okay? So what I'm going to say is let's let u equal to x minus 3, okay? And that means my du will equal dx. So that's something that we've seen before, okay? But this next part of the substitution is going to be a skill that we'll come back to tomorrow, but also a skill that can be really useful when we can't use u sub right off the bat in the beginning. And that is this. If I do the current substitution, I make this into a u, this becomes dx, but I still have an x on the top. In fact, I have 2x minus 1. So what I'm going to do is I'm going to take my u, and I'm actually going to isolate the x. So x equals u plus 3. And what that's going to allow me to do is everywhere I see the x, I can actually put in u plus 3. Okay? That's going to help me get rid of the x in the numerator. So let's see what this gives us when we substitute everything in. I have 2 times u plus 3 minus 1. So instead of 2x minus 1, I have 2 u plus 3 minus 1. Over, instead of x minus 3 squared, I have u squared plus 4. Okay. So take a quick moment and just make sure that all of those substitutions make sense to you. Like, where did things come from? Where did things go? And then we'll kind of start to use more algebra to finish up this question, okay? So any questions so far about where things came from or where things went? Okay. So I'm going to go ahead and distribute this 2. So I'm going to get 2u plus 6. And then I have this minus 1, okay? That's going to give me a numerator of 2u plus 5, okay? Because I had 6 and then I subtracted 1. Over u squared plus 4 du. Now I'm going to use the strategy that we use for a lot of questions with the partial fraction decomposition, which is I'm going to take this and I'm going to split it into 2 fractions. So when I split this into 2 fractions, I'll get 2 the integral of u over u squared plus 4 du plus 5 the integral of 1 over u squared plus 4 du. Okay. And what that gives me is 2 different types of integrals, just like we saw with partial fractions. That for this one, we're going to use u sub. Okay. And so my, let's call it v, is going to be u squared plus 4, and our dv will be 2u du. And that means I should have a factor of 1/2 somewhere in the front of that integral. Okay. This second one, which we are so good at identifying, is going to be our arctan. And like I said, it's not a bad idea to write down your a value. So especially if you're rushing on a test, you don't want to accidentally think a is 4. It needs to be the square root of that number. So a is going to be 2. All right. So let's take that first integral, see what we get. We're going to have 2 in the front and that 1/2. And we'll end up with the integral of 1 over v dv plus 5 times the integral of 1 over u squared plus 2 squared du. And that's going to give me natural log of u squared plus 4 from my first integral plus 5/2 the arctan of u over 2 and a plus c. Okay. Now, if you stop here, you're like 90% of the way there. You've done all of the hard work, and I want you to get full credit for this. So help me out here. You need to fully substitute back in, okay? That was one of the top mistakes that I saw on the quizzes this weekend, was that people stopped substituting back in. So if your question has X's at the start, you have to finish with those same letters, okay? So everywhere I see the u, I'm going to put in x minus 3. And that's going to give me a final answer of the natural log of x minus 3 squared plus 4 plus 5/2 arctan of x minus 3 over 2 plus c.
For 5 over 2 tan, arctan, how did you get the 5 over 2? Was it from the a equals 2? And we had to Take it
Yeah,
out.
A is 2, right? So it's going to be 1 over A in the front. That's where you get the 1/2. And then the 5 was already there, so 5 times 1/2 gives us 5/2.
Okay.
Okay. Yes, Alberto, you asked a great question. So the stuff from 9.4 wouldn't help here. And that's partially true. It's true in the sense that like we will use like the U sub and the arctan, like that ending part is kind of the same, but the starting part is really different in that I'm not splitting it into different fractions and trying to find like the numerators for those, but I'm trying to figure out how can I turn this into a situation where I can use U sub, and it's often helpful if we can complete the square to do that.
Professor, could we also do the, it's like you know how we have in the problem 2x minus 1 at the top, and at the bottom we have x squared minus 6x plus 13, and could we like change the top part to be the derivative of the bottom part and then separate them as fractions, like 2x minus 6 plus 5, and then separate like the 5 into another fraction, and well, you have 2x minus 6, and then like do U sub for that, and then do the completing the square for the other one.
Yeah, you can do that. I think that is valid. I think I'm trying to show you like if we want to say like if the question says use completing the square, here's how you do it. So yeah, there's definitely a little bit of wiggle room in terms of where you use that completing the square. And a lot of these integrals will have sort of more than one way to answer the same question. So.
Okay.
Okay, thanks, Alex. All right, folks. So let's go ahead and try example number 4, okay? And I really do appreciate these questions that folks are asking, like, how come we can't use this other method, all right? And so let's take a look at this one and kind of pick it apart, okay? So we've got 3x minus 1, in the numerator. And on the denominator, we have x squared plus 10x plus 28. So when I look at a question like this, I'm thinking, ooh, I could use partial fractions or I could use completing the square. How do I know which one? And so the very first question I ask myself is, can I factor the denominator? And right here, I notice that x squared plus 10x plus 28, there aren't a pair of whole numbers that multiply to make 28, but also add to make 10, all right? If there was, then I would say complete the square, or I would say partial fractions. But since there's not, I'm going to say complete the square, okay? All right, so let's go ahead and keep the numerator the way it is. And we're going to section off my ax squared plus bx. So I know what I'm trying to cut in half and square. And so this gives me 3x minus 1 over x squared plus 10x plus half of 10 is 5, and 5 squared is 25. So since I added 25, I need to make sure to subtract 25 on the back end to keep that bottom part the same as the original. And then I'll end up with the integral of 3x minus 1 over x plus 5 squared. And then 28 minus 5 is plus 3 dx. Okay. So let's go back to the beginning real quick, because I think I jumped right to here's why we don't use partial fractions, but maybe based off of the first few questions we looked at, someone might be out there thinking, well, how come we can't use U sub right off the bat, okay? So if we were to say, oh gosh, I don't really know what you'd use, and we were to try u sub, we would set our u to be the one with the higher power. And that would give us a du of 2x plus 10 dx. Now I look at my numerator. If this numerator said 2x plus 10, I would 100% use u sub. Or if this numerator said x plus 5, I would 100% use u sub. But it doesn't. So that's why I'm choosing a different strategy here, okay? And there's one last thing that I want to point out here. Some folks are starting to be creative algebraically in a way that is not quite legal. And so I just want to point out that when you find your du, there's really parentheses around this dx. And so you can't just subtract the 10 to the other side. The only real move you can make is divide a number away. And whatever you're dividing has to be the greatest common factor between all of your terms. So I could divide a 1 away, I could divide a 2 away, but I can't subtract 10 and move it to the other side, okay? So we really want to be careful about like where there are parentheses and where there are not. Okay, so we've got this in terms of our completing the square, all right? So we've completed the square, and now we're ending up with an integral that has 3x minus 1 over a perfect square plus 3. And so before we split our fractions, all right, let's look at what u sub can do for us at this stage. So like the other problem, we're going to let u equals x plus 5. And some people might even want to solve for x right here and have x equals u minus 5, right? And the reason why I'm doing that is I'm kind of looking ahead and saying, oh, there's an x up here, and I'm going to need to substitute that. And in this case, my du will equal dx, so I don't have to worry about a dividing factor anywhere. And so, like the last problem, let's substitute everything in. And so I'll end up with 3 u minus 5 minus 1 over u squared plus 3 du. And like the last one, let's distribute that 3, but also combine our like terms. So 3u. And then 3 minus times negative 5 is negative 15. And then I subtract another 1, so negative 16, over u squared plus 3 du. Now, at this point, now I'm going to split into two fractions. This will give me 3 times the integral of u over u squared plus 3 du minus 16 the integral of 1 over u squared plus 3 du. Okay. Now, as you work through these problems, you should notice a pattern that we're going to be looking at some kind of u sub or that inverse tangent one coming up again, okay? So this first one is going to be our u sub. So we'll say v equals u squared plus 3, dv equals 2u du, and dv over 2 equals u du, okay? And if we want to annotate here that we need an arctan, and we should probably even put that our a is not going to be 3. It's going to be the square root of 3, okay? I feel like in cases like the first one where that last number is a perfect square, everybody remembers to take the square root, right? We're like, it's not 4, it's 2. But for some reason, when we get to a situation where that last number is not a perfect square, we're like, huh, something must be wrong. I must have done something wrong. But it's okay for it to be the square root of 3 or the square root of 2 or whatever it is. You can just leave it like that, okay? All right, so let's see what happens when we integrate everything. So I've got a 3/2 the integral of 1 over v dv minus 16 the integral of 1 over u squared plus square root of 3 squared. Okay. And then from here, we'll have 3/2. 1 over v is our exception to the power rule, right? So natural log of u squared plus 3 minus 16 over root 3, because the 16 was there as a coefficient, but I have to divide by my a value. So 16 over root 3, the arctan of x, or not x, u over root 3 plus c. And then from here, all we need to do is plug back in. Everywhere we have our u, we're going to replace it with x plus 5. All right. Remember, you've done 90 to 95% of that work. Finish off the problem strong just by substituting everything back in. So we've got 3/2 the natural log of x plus 5 squared plus 3 minus 16 over root 3, the arctan of x plus 5 over root 3 plus c.
Quick question.
Yes.
If we were on a test and you know where you wrote out 1 over v, if we skip the next step and just plug our u straight on in, will we be penalized or get like the stink brow? Like how do you go from there to there?
Yeah, I would say that depends a lot on the kind of work that you've been showing on your quizzes, right? So if you've shown me in quizzes that you got this, then that's fine. But if you like didn't show me on a quiz that you got it, and then you try and skip some steps, I'm gonna wanna know where that came from.
Gotcha.
Okay? All right, any other questions about number 4 here? I would say though, again, like if you've been doing really well on these quizzes, I think a lot of us are at the point where we're like, we don't need to write out the whole u sub. We kind of know what we're doing here. Or we might not need to write that out, okay? But again, it is a case-by-case basis. So the work that you show me on those quizzes definitely reflects how I see you as a student and the kind of work that you're putting forth. Also, the kinds of questions that folks are asking in class help me understand you as individual learners better, okay?
I wasn't talking about that because writing out the u sub and the tan and the a just really helps you like
Okay.
be organized. I was talking about like when you wrote down 3/2 1 over v. If we went from that step directly to the answer where you just plugged in u instead of plugging in u for v and then plugging in the x minus for the u.
Yeah, that's totally fine. All right. So let's go ahead and do one last example before we take a break. Okay, so we'll take a look at example number 5. And then we'll have a short break. Okay. So example number 5 here, I noticed that my numerator has no x's. So right off the bat, I'm like, no way I can do u sub, because in order to use u sub, I would need an x on the top. But if I could get it into a perfect square situation, like this, then I could use arctan, okay? So as I'm looking at these problems, these are things that are helping make my decisions, all right? So I want us to know how to make these decisions ourselves as well. So no u sub for this one because there's no x in the numerator. So we're gonna go straight to saying, let's try and complete the square. So 7 over x squared plus 3x plus 3. That constant's just gonna hang out at the end. Now, it is possible that you'll see things that don't have whole numbers when we're dividing them in half and then squaring them, okay? So in this case, I have x squared plus 3x plus, let's see, half of 3 is 3 halves. Then if I square that, I have to square the top to make it 9. And I have to square the bottom to make it 4. So then plus 3 and then minus 9 over 4 dx. And then my last thing is to write it as a perfect square. So I've got 7 over x plus 3 halves squared. And then 9 minus 3/4 is going to give me, or 9 minus 3 minus 9/4 is going to give me 3/4. Okay. So I wanted to do a problem where we did have a case where our perfect square does not include a whole number, right? Most of the times these situations are like with a denominator of 2 or 4, okay? So it's okay if you end up with things that are halves and quarters. Now, from this, we can follow all the same steps. We can do a U sub. I don't need to solve for x in this case because there's no numerator x to sub out. And my du will be dx. And so when I substitute everything in, I'll end up with the integral of 7 over u squared plus 3/4 du. And I think this is actually a good time to write out, all right, I know I'm going to need arctan, but let's figure out our a, right? Because it's got a fraction, it's not even a perfect square. So I know that a is going to be the square root of 3 over 4, which is definitely okay if you write it as square root of 3 over 2, okay? So now all we have is one integral. We don't even have to split anything. I'm going to pull that 7 out to the front. I've got arctan of, oops.
Wait, do we multiply that by the square root of 3 over 2?
Yeah. 7 times 1 over a, so 1 over the square root of 3 times 2. And then our arctan of x, not x, u over a. Okay. Now, as gross as this looks, this part right here, I just need the reciprocal. Like anytime I say 1 over something, that's the definition of a reciprocal, okay? So when I simplify that coefficient, it's really saying 7 times 2 over root 3. And then I have my arctan. And everywhere I see a u, I want to put back in x plus 3 over 2. So again, the 2 over root 3 is because it's the reciprocal of that denominator, okay? Now, I've seen some folks get to something like this at the end of a really long problem and leave it here. That's totally fine, okay? I think the only things that might be worth cleaning up are 7 times 2 to make 14. And then maybe distributing that 2, only because that will make this fraction go away. So I get 2x plus 3 over root 3, okay? But either answer on an exam, if everything else is correct, either answer at the bottom will get you full credit, okay? All right, so there we have it, our first 3 examples doing completing the square. All right, so we're going to take a quick break, but when we come back, the questions that we're going to use for those are going to look at combining some of the completing the square with some of the trig substitution. Okay, so sometimes you'll get into a case where it might not be arctan, but you need another trig substitution from 9.3 to make it work. Okay. So it is 10:31 right now. Let's be back at 10:38. All right, let's be back at 10:38, and I'll go ahead and pause my video in the meantime. Okay. So before the break, we were looking at a lot of situations where everything had boiled down to a situation where it was like a squared plus x squared. And so we knew from that that it was going to be an arctan. Okay. Now we're going to take a look at a couple other cases that might take a little bit more work. And we want to be careful about how we know what's happening. Okay. So let's take a look at example number 6. Well, sorry, Monday morning. All right, so with example number 6, we've got a situation where we have the integral of 1 over x squared plus 8x plus 25. However, that denominator, that quadratic, is underneath a square root, okay? So what we're trying to do here is we're gonna go ahead and use completing the square to turn the inside into a perfect square situation. And then we're going to see how we can use some of the other strategies we've learned in this chapter to help us finish off the problem. Okay. So we're going to almost imagine for a little bit that the square root isn't really there. We're going to still write it, but as we do this algebra part, we're going to keep it the same as what we've been doing. So I have x squared plus 8x. And 8 cut in half is 4. And 4 squared is 16. So I've really got this plus 16 hanging out here. And then that means that my plus 25, and then I need a minus 16 at the end. Okay. I kind of did the first 2 steps in one step here. And now I'm going to go ahead and combine some like terms at the end, and I'm going to turn the first part into the perfect square. And then 25 minus 16 gives us 9. Okay. So we're actually going to go ahead and do a U sub right here, just to kind of maybe make the structure that we're looking at a little bit more evident. So our U is going to be x plus 4. That means that our du is dx. And that will give me the integral of 1 over the square root of u squared plus 3 squared du. Okay. So I've taken this integral, I've used completing the square underneath the square root part, and gotten to a situation where I have the square root of u squared plus 3 squared in the denominator. And so when we see this, okay, this u squared plus 3 squared, we should be thinking about some of the trig substitutions from 9.3, okay? And specifically in this case, we could say that u equals 3 tangent theta. And du is going to equal 3 secant squared theta d theta. Okay. So for better or for worse, the reality of a lot of these questions is that you often need more than one strategy to help you solve the question, okay? So we started off with the completing the square, and now we're going to use our trig substitutions to help us finish the problem, okay? One thing I want to point out that I've been super, super pleased to see is pretty much everyone is remembering to find the du and substituting that in. That has been, in general, that's a really hard thing to remember. So I'm so glad that you guys are doing that, because that makes the problems actually solvable. When you don't have that du, sometimes things get kind of weird, okay? So I love that we're already thinking, all right, I got to substitute everything in there, okay? Yes, go ahead.
I'm not sure why I can't see the last step. Why did you do the u equals 3 tangent theta?
Because this is from 9.3, where we're doing the trig substitutions, and when we see like an x squared plus a squared or u squared plus a squared, we need to substitute with the a tangent theta.
Oh, okay, thank you.
You're welcome. I know that was like the third day of class. It was so long ago, but a good review for the exam. Okay, so if you're already here, one thing that you might want to do is to go ahead and draw that triangle, okay? So the triangle, so that at the end, when you need to substitute everything back in, you already have the parts there. Now that I do want to point out, I would say maybe like 2/3 of us are doing that, but there's a third of us who are not doing this step right now, okay? So you're not getting a complete answer. So if you're in that 1/3, check over your quizzes. I did mark right on the quizzes so you can kind of see like where you maybe lost some points, but this part was definitely a big one. A lot of people lost some points because they didn't substitute everything back in, okay? So if we set this up, then we're gonna get tangent is opposite over adjacent, and we'll get the square root of u squared plus 9 as the hypotenuse, okay? All right, so now let's substitute everything in. And so we're gonna get the integral of 1 over 3 tangent theta squared plus 3 squared times, instead of du, I have to write 3 secant squared theta d theta, okay? Now, I've noticed that some of us are getting really confident in simplifying this step without showing the work, and I think if you are confident about that, that is fine on test day. But again, if your quizzes don't reflect that confidence, then I'm going to want you to show that work, okay? So this bottom part is going to simplify to 9 secant squared theta in the square root, and then next to it I still have the 3 secant squared theta d theta. And we want to make sure that we fully simplify before we start crossing things out. And so that's going to look like having the integral of 3 secant squared theta over the bottom is going to be square root of 9 is 3, square root of secant squared is secant, okay? And things that cancel, the 3's reduce to 1, and one of the secants reduces with the one on the bottom. And so we end up with the integral of secant theta d theta. And that is one of those like nice integrals to know. If you don't know that by now, then I would make sure that gets on that cheat sheet. Either way, I think it's a good thing to be on the cheat sheet. And we'll get the natural log of secant theta plus tangent theta plus c, okay? Now we actually have a few layers of substitutions that we have to put back in. So we need to change the thetas to have the u's, and then we need to change the u's to have the x's. And I'm going to show those kind of as two separate steps, but some of us might be able to do it in one step, and that's fine. So the natural log of secant is hypotenuse over adjacent, and tangent is opposite over adjacent. And so for the secant, I'm going to get the square root of u squared plus 9 over the adjacent, which is 3, plus the opposite, which is u, over the adjacent, which is 3, plus c. So again, some of us might like this intermediate step, and some of us, because we've been writing so much already for the problems, might want to jump straight to, all right, everywhere there's a u, I'm just going to put x plus 4. Okay. Now, I have seen some folks who, when they draw the triangle, they actually put the x's right in there so they don't have to do like a double substitution on the back end. And what I mean by that is it's okay if you draw your triangle and instead of u, you put x plus 4. And then this is still 3. And then this is x plus 4 squared plus 9. Okay, so either triangle works. The second one gets you directly to the answer. The first one, you have to do the u and then the x substitution. Okay, but find a way that works for you. Find a way that works for you and go with it. All right. Any questions on example 6? Okay.
Do you want us to rationalize denominators if we see a radicand in it?
No. I feel like you spend years of your academic career where people are like, rationalize the denominator, and then you get to Calc 2 and it's like, I don't know, you already did so much other stuff, just leave it. All right, so let's go ahead and move on to number 7, okay? So there is one tricky thing about number 7 that I just want us to be aware of, and the tricky thing has to do with signs. Okay, there we go. Okay, so if we take a look at number 7, we can say right off the bat, we're not going to use u sub like we did in number 6 because there's no x in the numerator. And then we're going to say, well, if I could factor the denominator, then my life would be easier. And maybe I could use partial fraction decomposition, but in this case, it's also under the square root. And so we can't use our partial fraction decomposition for these cases, all right? If it has a square root on the bottom, it's a little bit more clear cut that it's not partial fraction. But one of the things that I like to do is I do like to line up all the terms in order. Meaning I like to have, like, you see this x squared is kind of hanging out at the end. And like the 8 is first and then the 2x. So what we want to do is rewrite it so that negative x squared is in the front. So we'd have negative x squared plus 2x plus 8 dx. Okay. If you are a sign mistake kind of person, as I am, if you were a sign mistake kind of person, I highly recommend this step just so that you don't lose a sign somewhere along the way and end up with some weird numbers. But I think it was Patrick who asked earlier that really great question about what happens if the coefficient's not 1. And so just to kind of scroll back up for a moment, this case right here, we had a 2, so we factored it out before we did our completing the square. And what that did is change the number that we added or subtracted at the end, okay? So if we think about that mentality, and we look at number 7, what we should do to kind of follow that same pattern is factor out a -1 from the first term and the second term. So that's going to give us negative parentheses x squared minus 2x. And then that plus 8 hangs out at the end. Okay. Super easy here, makes sense here, but when you're doing these problems on your own, really something to look out for, okay? Because look what happens. This plus sign became a minus sign, right? So not just factoring out a number so the coefficients change, but also the signs are going to change. So now let's complete the square.
Would we have a -8 then?
I'm only factoring things out of the first 2 terms. And 8 is the last
But
term.
technically, there would be like another parentheses, right? Like,
Yeah. Okay, you can factor it out of the 8, but you're going to separate them anyway. So I think what that does is sort of like make more work for yourself. So I would focus on just changing the part you need to and not worrying about the other part. Okay, so negative x squared minus 2x. So -2 cut in half is -1. And -1 squared is 1. But if you rush and you do this, you're going to end up with the wrong number there. Okay? So what we need to do is we had the +1, but we really minused that 1. So if we subtracted 1, we don't want to subtract another 1. That's going to give us -2. We actually need to add 1. And let's bring it around back here and write this with the perfect square. So I'm going to end up with the square root of negative x minus 1 squared plus 9 dx, which doesn't maybe look as familiar to me as the tangent substitution in the previous problem, but what if we wrote it like this? Okay. Now, all I did here was say, instead of saying like -3 plus 2, I just said, hey, let's do 2 minus 3 instead. And what that helps me with is now that I see this, okay, I see an a squared minus something squared. That's going to tell me to use which trig substitution?
The sign?
Inverse sign.
Yeah, it's going to be the sine trig substitution, okay? So let's do a quick u substitution here to help us maybe see that pattern a little bit better. Okay. And then I can set up my trig sub. So u is going to equal 3 sine theta, and du will equal 3 cosine theta d theta. And that's going to leave me with 1 over the square root of 9 minus 9 sine squared theta. That's my u. And I need to have the du replaced with 3 cosine theta d theta. And so this is going to give me the integral of 3 cosine theta over that denominator simplifies to 3 cosine theta, which is super nice because now I can get rid of those. And really, I have the integral of 1 d theta. And we know that the integral of 1 is going to be theta plus c. Okay. And I got to do a few substitutions here. So maybe let's go back to this. Draw our triangle. I know that the opposite side is going to be u, or I could say x minus 1. I know that my hypotenuse is going to be 3. And I know that the adjacent side is going to be 9 minus u squared, or 9 minus x minus 1 squared. Okay. So again, choose which way you want to label your triangles, what works better for you, and go with it. So with the theta, I noticed that I had the sign in the beginning, so I'm going to do an arc sign here, but I do appreciate I've seen a variety of substitutions for theta on the quizzes, because more than one answer can definitely be right. So I'm going to say this one is going to be the arc sign of u over 3 plus c, or the arc sign of x minus 1 over 3 plus c. Okay. So the situation where we're doing these integrals, and after we complete the square, we might need a trig substitution from 9.3 to help us out. Okay. Questions on example 7?
How did you change that denominator to 3 cosine theta?
Oh, okay. So yeah, let's go back and fill that in. So this part is the same as the square root of 9 times 1 minus cosine squared, which is, sine squared, which is 9 times cosine squared. And then that gives you 3 cosine.
Sweet. Okay.
Okay. All right. Well, let's go ahead and do one last example right here. Okay. So with this example, a few things. I don't see any fractions, so I'm definitely not choosing between completing the square and partial fraction. I also don't see an x on the outside of that square root anywhere, so I know no u sub. Which leaves me with completing the square. Okay. So let's complete the square, see what happens. I've got x squared plus 4x. Half of 4 is 2. 2 squared is 4. The plus 5 that was there, and then a minus 4. Okay. Now all of that is underneath the square root. Now let's write it so we can see that perfect square better. So x squared plus 4x plus 4 gives you x plus 2 squared. And then 5 minus 4 is 1, so plus 1 dx. Okay. I'm going to make a quick use of here. So that maybe I can see the structure of this integral a little bit better. Okay. Now, given what's happening underneath the square root, which trig substitution from 9.3 would be best here?
Tang.
Yeah, that tangent one, exactly. Yeah, Dominic, I'll go back to that one after we finish this example, if that's okay. Okay, so we've got u equals 1 tangent theta. You don't have to write that one. Du equals secant squared theta d theta. And we're going to go ahead and substitute that in. Tangent squared theta plus 1 times secant squared theta d theta. And again, that secant squared theta d theta, this is my du. That's why there's so much extra there. And then this was my u squared plus 1. Okay. Now, again, some of us might know right off the bat that this square root is going to simplify to secant, right? But the reason why that is because tangent squared plus 1 is equal to secant squared. And it's underneath the square root, which means that it will be secant theta. So I have secant theta from the square root part times secant cubed theta, nope, secant squared theta from the du. Okay. Now we end up with a situation here where we end up with secant cubed theta. Now we know the integral of secant. We've seen that one a lot. Secant has an integral of natural log of secant theta plus tangent theta, but we haven't seen that secant cubed, all right? And we did that in one of the example problems when we did the trig substitution, but I want to do it again here because I think it's a good reminder of what we learned on the very first day last week, which is we're going to go ahead and use integration by parts, okay? So this we're going to solve using parts. So when we solve that using parts, we want to remember the formula. The integral of u dv equals uv minus the integral of v du. Okay? That's definitely a formula you should have on that cheat sheet for Wednesday's test. So now we might have seen one case of this since we did this before, but most of the integration by parts that we've seen have two different kinds of functions. So we have like a polynomial and we have a trig, or we have an exponential and we have a polynomial, or we have a natural log and we have a trig. So it's been like two different kinds of functions. But we can actually use integration by parts when we have the same kind of function, like they're both the same level. So in this case, they're both trig ones. So how do you know which one's going to be your u and which one's going to be your v? So the way that we decide is not necessarily scientific, but we say I know I have to take a derivative and I know I have to integrate. So the one that's easier to take the derivative, that's going to be my u. And the one that's easier to take my integral, that's going to be my dv. That's literally how we make that decision, okay? So again, The one that is easier to take the derivative, pick that for your u. The one that is easier to take the integral, pick that for your dv. So I see that I have a secant theta, and I know that derivative, so I'm going to put that as my u. And I know that the secant squared theta is something I know the integral of, is tangent, so I'm going to put that as my dv. So du is going to equal secant theta tangent theta d theta, and my v is going to be tangent theta. And now we're going to put all of these into our integration by parts formula, which will give us secant theta, that's my u, times v is tangent theta, minus the integral of v du Now this simplifies to the integral, the integral of secant theta times tangent squared theta d theta. Okay. And this loops us all the way back to 9.2, where wherever we have that tangent squared, we can replace it with one of the Pythagorean identities, secant squared minus 1. So we've got the integral of secant cubed theta d theta equals secant theta tangent theta, that's my uv part, minus the integral of secant theta times secant squared theta minus 1 d theta. All right, I'm going to pause for a moment here, just give you a chance to finish writing and kind of like thinking about this. I know this is definitely a big juicy one to finish off the end of class with. Now, when we're approaching this last integral, we're going to want to distribute that secant theta. So we'll end up with the integral of secant cubed theta d theta equals secant theta tangent theta minus the integral of secant cubed theta d theta, and then minus the integral of secant theta d theta. Okay, so I kind of did two things in one step there. I distributed, but I also split it into two different integrals. The reason why I did that is because now I can see that this is a like term with this one. So I can simply add that one to the other side. All right, so this one, we know, integral of secant is that natural log secant theta plus tangent theta. And then I'm going to divide everything by 1 or by 2 to get a 1/2 on that right hand side. All right, So from here, okay, we've got a few things that we need to take care of. We've got, let me put brackets around this. We've got our integral. We have an answer, but it's in terms of theta. And if we scroll back up, we have x's in our original, so we need to make sure we have x's in our answer, okay? So let me go back over here to here and think about the triangle. So I know that my opposite is u, or x plus 2. I know my adjacent is 1. And therefore, my hypotenuse is x plus 2 squared plus 1. And so I can use those values to substitute my thetas here so that I end up with x's in my final answer, okay? So secant is going to be hypotenuse over adjacent. Tangent is going to be opposite over adjacent, and I'm going to be multiplying them. This secant is going to be hypotenuse over adjacent, and this tangent is going to be opposite over adjacent, but this time I am adding them, okay? Now I know you guys know the difference to that. I think there were a few folks, and I could tell you were like so tired by the end of the problem that sometimes the multiplication and addition got lost, but we want to make sure we know, are we adding or are we multiplying? So let's see what we get for a final answer. We have 1/2. Secant theta is hypotenuse x plus 2, sorry. Hypotenuse over adjacent times the opposite over adjacent plus the natural log of hypotenuse over adjacent plus opposite over adjacent. Now, if this is how you finish your, question on an exam, and you're like, my hand is tired, I don't want to rewrite it without all the ones, that's fine. If you want to, you can certainly rewrite this without the denominators because all the denominators are 1. And so either one of those would be fine as a final answer. All right. So there's our whole question on one page there. Lots of writing, I know. I'm going to go ahead and go back to question number 7 real quick. Somebody had a question about where the arc sign came from. So I just want to make sure we're all really clear on that. Okay. I'm going to zoom back out or in, and let's go back to here. So I think when you're trying to substitute everything back in at the end, I find my original trig sub to be really useful. What I mean by that is I said that u could equal 3 sine theta. So u over 3 equals sine theta. Or we could say that theta equals arc sine of u over 3. Okay, so because I had already written my equation for that included the relationship between the sides, I just go ahead and use this to help me plug in for my theta. Does that clarify that? Okay, great. All right, so another pretty algebra intensive day here. Lots of completing the square. And again, completing the square is an algebra strategy that we're gonna use again when we get to chapter 12. So it's definitely a good one to invest in. Other than that,
Hey, Professor.
Yeah, go ahead.
I'm sorry. For number 8, our theta would be inverse tan. Or what would our theta be for
Great question.
number 8?
So you could write a few different ones. Here, let's go down here. X plus 2. Okay, so if this is your triangle, here's a few different ways that you could write your theta. You could say that theta equals the inverse tangent of the opposite over the adjacent. You could write that. You could write that it's the inverse sine of the opposite over the hypotenuse. Okay, so we have our opposite over adjacent. We have our opposite over the hypotenuse. You could go kind of crazy and be like, ooh, I want to throw a cotangent, and that would just be adjacent over opposite. You could say, arc sine is too boring, let me do arc cosecant, and that would be the hypotenuse over the opposite. Or you could say, well, I want to use arc cosine, and arc cosine is adjacent over hypotenuse, so 1 over. Something like that. Or you could be super fancy and say, I'm going to use arc secant, and it would just be the reciprocal of that.
Cool, thank you. I just wanted to know if we had to use a specific one.
No. So that was actually the cool part when I was grading this quiz number 2. Some people chose like cosine for one of the questions. Other people chose secant for the same question. So it's really up to you.
Cool, thank you.
You're welcome. Okay. Any other questions about today's lesson? I know there was a question on number 9 on the quiz, which I'll definitely go over. But are there any other questions on 9.5 stuff? Okay, so how many questions are going to be on the first test? I think there are 6, but there are different parts to the question. So I would say more like 12 to 13 different integrals. Cool. All right, Gabby, did you want to go over number 13 on quiz 2?
Yes, quiz 2.
Okay, perfect. All right. Well, folks, if you don't have any more questions on today's lesson, you're free to take off. If you want to stick around, we're going to answer number 9 and number 13 on quiz number 2, and then see what other questions pop up. Okay? All right, folks, have a good rest of your day if you're taking off.
All right. Thank you so much.
All right. Bye, folks.
Thank you.
You're welcome. Okay, so I know for quiz number 2, for question number 9, it was like finding the A, B, and the C and D that were tricky for folks. Gabby, for question 13, was it kind of the same issue, like finding your constants, like your A, B, C, D, and E?
Yeah, it was.
All right, cool. That's what I figured. So let's kind of take those parts alone and work on those, okay? So I'm going to go ahead and share my screen. Okay. And we'll start with number 9. But I'm going to write it down here. Okay, so number 9, we started with x squared minus 29x plus 5 over x minus 4 squared times x squared plus 3x dx. And so based on that, we have a linear factor that happens again. And we have an irreducible quadratic. So that's why we need the setup to look something like this. Okay. Now, from here, are we okay jumping to the equation that is the numerators only?
Yeah.
Okay. So x squared minus 29x plus 5 equals a times x minus 4 times x squared plus 3 plus b only needs the x squared plus 3 plus cx plus d needs x minus 4 squared. Okay. And with this one, I could plug in a 4 to find b, okay? So we could definitely start with that. So 4 squared is 16 minus 29 times 4 plus 5 is going to give us negative 95 on the left-hand side. And then on the right-hand side, we're going to have b times 16 plus 3, which is 19. And this will give us a b value of negative 5. Okay? Now, unfortunately, that's the only variable that we can find using this pick a clever number. So the rest of it, we kind of have to do with brute force, okay? So I'm going to go ahead and write the right-hand side. And I'm going to take this step by step here. So let's FOIL this before we distribute the a. X cubed minus 3 plus 3x, so outer terms, minus 4x squared, that's the inner term, minus 12, plus bx squared plus 3b plus cx times d, or plus d, times x squared minus 8x plus 16. Okay. So let's distribute our a's to those 4 terms. And let's FOIL the last part. All right, what do we have here? We have cx cubed minus 8cx squared plus 16cx, and then plus dx squared minus 8dx plus 16d. It's supposed to be an A. Thank you. Okay, so now it's an A. This is the great point to stop, double check your work, and make sure that all the distributions are correct, all right? And then one of the things that I find helpful is writing all the mini equations, okay? So I'm gonna start off with the highest power. And I noticed there's no x cubed on the left-hand side. So that means on the left-hand side, the coefficient for x cubed is 0. Now I'm going to collect all the terms on the right-hand side that have an x cubed. So a x cubed plus c. And that's it. I'm going to do the same thing for each of the powers. So 1x squared equals negative 4a plus b minus 8c plus d. All the linear terms. Negative 29x equal, negative 29 equals 3a, no b's, plus 16c minus 8d. And then the constants. 5 equals negative 12a plus 3b plus 16d. So again, I would stop here on a test and just make sure that I've pulled all the right coefficients, all right? And when I take a look back at my answer key, I've got 0 equals a plus c, 1, da, da, da. Okay, so it looks like I've got all the terms here. From here, we just need to solve this system of equations, okay? Now, if you've already found one of the numbers, you're welcome to plug that number in everywhere you see that letter. So for example, I might write this as 1 equals negative 4a minus 5 minus 8c plus d. And that would become 6 equals negative 4a minus 8c plus d. Now, there's no b to plug into the third equation, but there is in the fourth one. So 5 equals negative 12a plus 3 times negative 5 plus 16d, or that's going to be 20 equals negative 12a plus 16d. Okay. Now, there's so many ways to solving systems of equations, especially ones that have more than like 2 or 3 letters. And so what I like to do is kind of start to pick the simpler equations and see if I can get rid of more letters. Like right now we have 4 equations and 3 unknowns. Like we already found B, so we only have 3 things that we don't know. So my strategy is going to be now to say, let's take the simplest equation, 0 equals A plus C. And I'm going to write this as A equals negative C, right? I just subtract the C to the other side. Now what that means is everywhere I see a C, or everywhere I see an A in the equation, I can replace it with a negative C. And then I'm going to end up with equations that only have C's and D's. So let's see what our equations look like after we do that. We've got 6 equals negative 4. Instead of A, I'm going to write negative C minus 8C plus D. Well, that equals 6 equals, this is 4C minus 8C is negative 4C plus D. Well, that looks like a much nicer version of the equation, okay? And let's go ahead and do the same thing with the last equation. So I've got 20 equals negative 12 times negative C plus 16D. So I get 20 equals 12C plus 16D. Okay. Now the beauty of this is now I've got 2 equations and 2 unknowns. At this point, I find that elimination is a little bit faster than continuing to substitute. So I'm going to take the top equation and I'm going to multiply it, so times 3. That's going to give me 18 equals negative 12C plus 3D. And I'm going to keep my bottom equation the same. 20 equals 12C plus 16D. And the reason why I multiplied by 3 is because now when I add the fraction or the equations together, the C's go away. So 18 plus 20 is 38 equals 19D, and that gives me D equals 2. All right. So I found my B and I found my D. What might be a good letter to find next?
C?
Yeah, why is C a good letter to find next?
Because we already have A and D. I mean,
we don't have A yet.
Yeah, I lost my thought.
Okay. Anybody else have a reason why it's probably a good idea to find C at this point?
We already have an equation with just D and C.
Exactly, exactly. So we're sort of like backtracking here, right? So we've got our D, and we have so many equations that have a C and a D and no other letters, which means now we can find C. But I would say the easiest one is probably this one, and just because the coefficients are the smallest. However, you could use this equation too. It doesn't really matter, okay? So 6 equals negative 4C plus 2, or 4 equals negative 4C, or C equals negative 1. Okay. So I've got B, I've got D, I've got C. What's an easy letter to find next?
A.
A. And that is the only letter left, right? So it's not like, well, how many are we choosing from? But I would say maybe a reason why it's easy to find A is because of this equation. I know if I know C, I know A. And so this gives me A equals 1. Okay? So if I do this, then we've got sort of a more explained situation about how all these things happen, okay? Now, if you look at the answer key, this is different from the answer key. There are a lot of different ways for solving them, okay? And part of it is kind of playing around and seeing what strategies work and what strategies maybe take a little bit longer but still work, okay?
Okay, thank you. This helped a lot. I don't think we have to go over 13 now.
Okay, cool. And do you pronounce your name Alina or Alana? I don't want to say it wrong.
It's Alina.
Okay.
You actually got it right.
Okay. I was like, or neither of those. Then tell me the right way. But okay. All right. Cool. All right. So I hope this was helpful. I did include it in the lecture video. So if you want to go back and kind of listen to it again, or if you had friends who couldn't make lecture today, then they can also see where some of those numbers came from. Okay.
Rosa, can you do number 5 before you leave?
Yeah, number 5 on this quiz.
Yes, please.
Okay. Let's go back up to number 5. Okay, this number 5?
Specifically, could you do the secant substitution, because that's how I did it, and I keep getting a coefficient that you don't get.
Okay, okay. So let's copy this problem now. Sorry. Stop calling me. Who are these people? Okay. All right. So let's copy this problem. I wonder if we could even squeeze it in here. So if we wanted to use a secant substitution, we could say that x equals 3 secant theta and dx equals 3 secant theta tangent theta d theta. Okay, so now let's substitute in. We'll get 3 secant theta, and then the square root of 3 secant theta squared minus 9. And then we need at the end 3 secant theta tangent theta d theta. Do all those substitutions look like what you had?
Yep, so far so good.
Okay, so then 3 secant theta, this is going to become 3 tangent theta times 3 secant theta tangent theta d theta. And then we'll end up with a 27 on the outside, and then secant squared theta tangent squared theta d theta. Okay. So we could actually use a u sub here. And we could say that u equals tangent theta. That would make du equal to secant squared theta d theta. And that will give us 27, the integral of u squared du, which is 27 over 3 u to the third plus c equals 9. U is tangent theta to the third plus c. Okay. And now our tangent theta, we would want to draw a triangle. We have our theta. Secant is hypotenuse over adjacent. X squared minus 9. So our tangent is going to be opposite over adjacent cubed. So this cube has to get distributed to the top as well as the bottom. So we'll end up with 9 times x squared minus 9 to the 3/2 over 3 cubed is 27. And that's how we get the 1/3 x squared minus 9 to the 3/2 plus c.
Okay, I see what I did wrong. Thank you.
Okay, you're welcome. All right. Any other questions out there, folks?
Professor, for the quiz number 3, on number 3, so like we would do completing the square first and then a u sub, right?
For question number 3, yep, completing the square and a u sub, exactly.
And then we distribute first before we do the sign trig substitution, right?
Yeah. Very good. I love the way you're able to summarize that process.
I was doing it just now and I forgot to do the u sub for, or the x substitution at first, and then I went on with it and I was lost on my own work.
Oh no, okay. All right, folks. So that's where we're going to call it for today. I'm going to go ahead and stop the share and stop the video.